So we're very happy to have Raquel Perales from Oaxaca to give a presentation on the intrinsic flat stability of the positive mass theorem for graphical manifolds.
So thank you very much for the invitation. And we're going to talk about the stability of this theorem that Lan just presented. So this theorem was proven first in the spin case and then in other cases. And the last proof was shown by Huang, Yang, and Martin. And it says the following: any complete asymptotically hyperbolic Riemannian manifold, N with a Riemannian metric G. And here N can be bigger than 3 with scalar curvature bounded below by minus N multiplied by N minus 1 satisfies that the mass, and this mass was defined by Lan, is non-negative, and the quality holds if and only if this manifold is isometric to the hyperbolic space. So what we are going to do in this talk is take a sequence of manifolds, so MJ, that are going to satisfy the conditions of the theorem, and we want the mass to converge to 0. So if their mass converges to 0, we could expect that in the limit, if we have some nice distance, then we will get the hyperbolic space. And in order to define this limit, we are not going to use Gromov-Hausdorff limit, nor C0 distance of the Riemannian tensors, because sometimes there are sequences that have scalar curvature bounds, but do not converge in GH sense, but they will converge in intrinsic flat sense. So we are going to use here the intrinsic flat distance. And we will define a class of asymptotically hyperbolic Riemannian manifolds in which we will have this as a limit space. Okay, so this is just motivation. I will give the definitions later, but the class of manifolds that we will consider are manifolds that are embedded in the hyperbolic space of dimension n+1. So this C is an isometric embedding. And furthermore, our manifold, once that it's embedded, we can see it as a graph of a function f. So here's my function f, and f is continuous up to the boundary, and f is smooth outside the boundary. And here U can be empty, or it can be non-empty. Okay, so when it's empty, we say that our graph is entire. And so our manifold is going to look like this manifold because it's a graph, and here we see, I mean, this part corresponds to U. Here the function is not defined. And what we are going to do actually, instead of proving that the whole sequence of manifolds M converge to the hyperbolic space, we are going to study these smaller regions of our manifold. So this small region of our manifold is basically take your manifold and intersect it with the cylinder BBR times R. So I'm intersecting our manifold with this infinite cylinder, and I get this region. Okay, so what we are going to do is the following. So we are going to define a class of manifolds that are going to be asymptotically hyperbolic, and we will prove that given a sequence in this class with mass going to 0, then these regions that I defined in the previous slide will converge in intrinsic flat sense to the ball in the hyperbolic space. Okay, these other two things is like notation of intrinsic current spaces. I will say later what this means, but for the moment we have convergence of these regions to convergence of this ball in the hyperbolic
one question.
space.
So you assume some manifolds with their induced Riemannian metrics have metric scalar curvature greater than the hyperbolic space.
Yes.
But wouldn't make them flat, convex, I'm sorry.
Yes. So in this part is actually
so your picture is confusing. They're not like that, they're convex.
No,
they scalar curvature, I think, well, potentially can make them convex. I just want to understand it.
No, they are not. No, these regions are not convex, and that's why I have to use this distance.
So they don't have to be convex. I'm just not certain. Okay.
Yes. And well, other people have studied this type of results, and here I just wrote some of them. And these results that I mentioned only use intrinsic flat convergence.
But what worries me that when you have induced metric of positive scalar curvature, I don't have clear picture what it signifies and wouldn't make it convex in this case. Okay. You say no, you say I want to see it in simple cases.
Yeah, I mean, what do we have?
In dimension 2 and 3, for example, it may be convex, right?
Yes.
In dimension 2 and 3, it will be convex.
Yeah.
So for surfaces, it can be only convex. Correct?
Yes, correct. I mean, but now
so this picture cannot happen in dimension 2. In dimension 2, it will be convex.
No. In dimension, no, we are thinking about dimension 3 or higher.
Yeah, no, ambient space dimension 3, but your submanifold.
No, ambient space should be dimension 4. Because,
okay, it might be 4 at least. Okay.
Yes.
Then it's okay, probably.
And then, I mean, once that we prove that these regions converge to a ball in the hyperbolic space, we can also prove a pointed version. So we can prove that actually the balls in our manifolds, in our graphical manifolds, with the distance of the manifold, converges in intrinsic flat sense to the ball in the hyperbolic space with the distance of the hyperbolic space.
Right. Yeah, in high dimension, don't have. Okay, now I see. Yeah. Thank you.
And this is actually what we are going to do. I'm going to tell you what this class is, and I'm going to tell you what this intrinsic flat limit is. But before passing to all the details, I just want to make this historical note, because the class that we are studying actually was studied first in the asymptotically flat case. So it was introduced by Huang and Lee, one class that is actually a big class. So let me call it GN. And here I'm going to put RN because it's in the flat case. Okay, so they introduced one class of manifolds. And in this class of manifolds, they studied stability of the positive mass theorem, but with respect to the flat distance. So Federer-Fleming flat distance. And then Christina-Sormani came and they restricted this class to a smaller class that I'm going to call GN RN. This also depends on some parameters, R0, gamma, alpha, D. And here they studied stability of positive mass theorem with respect to intrinsic flat distance. Intrinsic flat distance. Okay, and then what happened later is that we found some gap in this theorem, but the theorems that they presented are correct, and they are corrected in this series of papers. So one with Allen and myself in the entire case. So when we don't have, when boundary of U, or when U equals the empty set, and then in the other case with Huang and Lee. And this is using a completely different proof of what Huang and Lee-Sormani had in mind. So this is very different. And then with Del Nil, we prove what Huang, Lee, and Sormani wanted to prove. So we fill in that gap. Okay, and this is in the asymptotically flat case, and then one can adapt all the conditions of this class and then introduce a class in the hyperbolic case, and that was done by Cabrera Pacheco. and then study the stability of the positive mass theorem with respect to flat distance. So that's what Cabrera Pacheco did. And then Cabrera Pacheco, Graf, and myself studied the stability of the positive mass theorem for asymptotically hyperbolic manifolds with respect to the intrinsic flat distance. So this is just the historical remarks, how this class comes into place.
But may I ask one question? Because you say it's abstract, there's abstract flat topology, but here it probably converges like a current in this ambient hyperbolic space. It will be just usually.
Yes, I mean, once that,
flat topology in this space, right? There's a current.
Yes.
Correct?
Yes, I mean, but in intrinsic flat sense, once that you have, convergence, you can embed everything in one single
intrinsic,
space.
it's kind of extrinsic. Extrinsic, namely in the ambient hyperbolic space.
Yes, yes.
Okay.
Mm-hmm. That's what Huang and Lee did?
Yes, and what Cabrera Pacheco is Federer-Fleming flat distance in Hn plus 1, and Huang and Lee Federer-Fleming flat distance in Rn plus 1. Yes. Okay. So now let me just tell you the overview. Now I will give a lot of details. So I'm going to talk about intrinsic flat convergence. Then I will describe the class that we are studying, and finally sketch the proof of the theorems. So intrinsic flat convergence. So for intrinsic flat convergence, we actually need some currents, and these currents are going to be defined in a complete metric space set. And these currents were introduced by Ambrosio and Kirchheim. And they are multilinear functionals that take coordinates, take an n+1 tuple in this set, and it goes to R. Okay, and these currents satisfy certain conditions, which I'm not going to mention now, but this current give us some mass measure that is T double bar in our metric space set, and then we can talk about the total mass of our current. So the total mass of our current is just evaluate your measure on the whole space set. And I'm not giving the definition of current because actually I'm more interested in these currents, in integral currents. So integral currents are going to be currents such that its boundary is a current, and they can be written in this way. So this way is the following. So we have some weights here that I'm denoting by theta I. These weights have to have integer values, non-zero. And then this function f, which is my Lipschitz function that is bounded, here I put it here. So this is like the weight of the integral. And then this pi, with this pi, I create some Jacobian. And the only thing that I need to do, I need some type of charts. These charts that appear here, these 5 i's, are just by Lipschitz maps. And actually, this can be done in such a way that the images of these 5 i's can be pairwise disjoint. So an integral current looks like this. So these are the currents that I'm interested in. And then, in order to define intrinsic flat convergence, what one needs is to know what is an integral current space. So an integral current space, well, it will be a triple xdt, where xt is a metric space, t is a current, but t is a current in the completion of my metric space xt. So it's an integral current there, and the relationship with x and x bar, or what should happen, the relationship between x and t should be the following one. So here set t is just the points in x bar such that its positive lower density with respect to this measure is positive. Okay, So basically just think that the support of T, this is what equals to X. That's one way of saying this. And then the main example, well, comes from Riemannian manifolds. And given a Riemannian manifold that I want it to be oriented and compact, then we can define an integral current space in this way. So I put M, the distance coming from the Riemannian tensor G, and then this current, well, it will look like this type of currents. And here I have to choose weight equal to 1, okay? So it comes from a by Lipschitz oriented atlas on M, and we choose theta's AI equal to 1. And with this definition, well, the mass measure just coincides with the volume form. The total mass of the current is just the volume of the manifold, and the boundary of this current is just the current of the boundary of M. Okay, so now we know what are our spaces in which we are going to define this intrinsic flat distance. So this intrinsic flat distance takes two integral current spaces. They have to be of the same dimension. And then in order to calculate their distance, one embeds each of them in a bigger space set, possibly bigger space set, and one embeds them with, these are isometric embeddings. And then once that we are in set, one has to calculate the flat distance of the currents, of the push forward of the currents. So phi1 push forward T1 and phi2 push forward T2. And the infimum here will be taken among all complete metric spaces set in which one can embed the spaces xi. So this is the distance. And the only thing that now I need to define is what this distance means. So the flat distance is as follows. So now we are in a fixed space set, and here we have two currents. So given these two currents of the same dimension, so they have dimension M, we can calculate their distance infimizing over the mass of U and the mass of B. And here U and B should be all possible currents such that we have this equality. So this is the example, and all my pictures are taken either from Cristina Sormani's papers or the papers of Huang-Lee and Huang-Lee or Cabrera Pacheco. So this is from Cristina Sormani. So anyway, this is my main example. Here I have current associated to T1, so it's integrating over this red line, and T2 is integrating over the blue line, and they are oriented in this way. And then a possible B and a possible U is given by this two-dimensional region that is in yellow, that's V, and then this green part will correspond to U. And I have to endow them with the right orientation, so then this equality holds. Okay, so this is our flat distance. And once that we know what is the intrinsic flat distance, here is a theorem by Sormani and Wenger saying that actually this function is a distance, but what one has to do is identify certain integral current spaces. So this is not very unusual, because if you remember in Gromov-Hausdorff distance, if the spaces are isometric, then their distance is the same. So in this case, we say that two integral current spaces will be equivalent if there is an isometry between x1 and x2 that takes the current T1 into T2. Okay, so that's our theorem saying that this is indeed a distance. Okay, and then Wenger prove a compactness theorem. This compactness theorem actually holds for integral current spaces, but I just wrote it for Riemannian manifolds. But then this theorem says, if you have a diameter bound, a volume bound, and an area bound, uniform bounds, then given this sequence, you will have a converging subsequence. And the the limit is going to be an intrinsic, an integral current space. Though in the case of Riemannian manifolds, even if I start with Riemannian manifolds, the limit is only going to be an integral current space. It's not necessarily a Riemannian manifold. Okay. And now for the stability theorem that I would like to prove, we actually only need this theorem, which was proven by Brian Allen, and myself. And this theorem says the following. So what we are actually going to do is fix our topology. So fix the topology means fix your manifold M. And we want this manifold to be compact, oriented, and to have non-empty boundary. And then we have a special Riemannian tensor, Riemannian metric G0, and we want our manifold M with this Riemannian tensor G0 to be to have a totally convex interior. And that only means that given 2 points in the interior, I can connect them by a geodesic, and this geodesic has to lie completely in the interior, okay? So I want this to happen. And then I also have a sequence of Riemannian tensors, Gj, and this Gj only need to be continuous, okay? This sequence of Riemannian tensors is also defined on the same manifold M, because I'm fixing the topology of my sequence. And then if the following 4 conditions are satisfied, I can say that the manifolds Mj converge in intrinsic flat sense to M0. And here again, Mj is just the manifold M with the Riemannian tensor Gj. Okay, so one should notice that actually one needs these conditions in order to have a compactness theorem, as I showed you here by Wenger. So one needs these conditions. So actually these 3 conditions are, well, not that bad, but in order to ensure that actually the limit is M0, we really require this condition. This condition is very important. It can be weakened a little bit, but this condition is like super important in order to ensure that we have this limit. And basically, this is the theorem that we are going to use to prove our stability result. Are there any questions before I move on to present the definition of the class of manifolds? Well, if not, let me just tell you that a similar theorem was proven by Allen-Sormani and myself, but this theorem was in the case in which the manifolds were closed. Okay, so now let me introduce the class of asymptotically hyperbolic Riemannian manifolds that we are going to study. And as I told you, what happened first is that Cabrera Pacheco introduced a class, which I'm giving the definition here. And with this class of manifolds, he proved stability with respect to Federer-Fleming flat convergence in Hn plus 1. Okay, so let's see what this class is. So as I told you, these are going to be graphical manifolds. They are going to be contained in the hyperbolic space. And here the hyperbolic space, I'm writing it in this way. Okay, so here B, I haven't said it, but B equals only depends on some radial function, and it's going to be the hyperbolic cosine of R. And in this, here I have the metric B bar, which is going to be the metric in Hn plus this warping function ds squared. Okay. So my manifolds are contained in Hn plus 1, and they should satisfy the following 3 conditions. Well, they have to satisfy several conditions, but first, graph F, we want it to be a balanced asymptotically hyperbolic graph. So this means that at infinity, it looks like hyperbolic space of dimension n. We require that the scalar curvature of graph of F is greater or equal than minus n times n minus 1. And I didn't say this, but here graph F, we can give it the Riemannian tensor, which is induced by being contained in Hn plus 1. Another thing that we are going to require is that this manifold is either entire, and entire, remember, it means that U equals infinity, so there is no boundary, or if it has a boundary, so that means boundary of U is different than 0. So if it has a boundary, then, sorry, empty set, then this boundary has to be a minimal boundary, okay? So meaning partial of U has to be minimal.
So it's a minimal hypersurface.
Yes.
Thank you. Inside the graph, yes, thank you.
Yeah. Well, yeah, and this, I mean, just basically means that the gradient of F, or the norm of the gradient of F, is going to converge to infinity when we are approaching the boundary. Maybe I have to multiply by the b squared, but it means that the function there, when it approaches the boundary, is going to infinity. Mm-hmm. That's going to ensure that boundary of U is minimal. And then in addition, we require the following 2 conditions that I enumerated, 1 and 2. And one is that the mean curvature vector of graph F points upwards. And number 2 is that the level sets, or almost every level set, is star-shaped and outer minimizing in Hn. So this is the class that Armando Cabrera Pacheco studied. And it's very similar to the class that Huang and Lee studied for the asymptotically flat case. Here I'm just telling you how the mass is defined, but this was actually explained by Lan. So this is the mass. And here, what one has is this E. And this E is basically, well, measuring the difference between the hyperbolic space, between the Riemannian tensor of the hyperbolic space and our graph. And remember that our graph, actually, I can also put the Riemannian tensor G, which is G Hn minus plus d squared df tensor df. So basically this E is this hyperbolic tensor minus this hyperbolic tensor. And that's what gives me the mass. So we have to ensure that this thing converges, and it will converge to the mass. But in the case in which we have a graphical manifold, the mass can be rewritten in this following way. So in this case here, I just have the difference between the scalar curvatures of the hyperbolic space. Here is the difference, and the one in my manifold. And here I have the part that comes from the level set of our manifold, of our function f. And here I have, well, the cosine, hyperbolic cosine, the gradient of f, and here I have the mean curvature of our hypersurface sigma h. Okay, so from this very nice
Could I ask a question? Is it
yes.
Is it obvious if this function is continuous with respect to the topology you're working with?
This function meaning f, or this function meaning what I'm integrating?
No, the function which gives you the mass. Isn't it the function that gives you the mass of this thing?
This part, right?
Yeah, that's right. Is that?
Yeah, I mean, I am skipping some, some stuff when you define what it means to be a asymptotically hyperbolic graph. Then it will give you the conditions that actually makes this limit work.
So it is continuous.
Yeah, I guess.
I think it's not.
No.
So, I think this is, if I understand Jim's question correctly, if your sequence of manifolds, I don't know the graph case, but in general, in the asymptotically Euclidean case, if you have a sequence of manifolds converging in the intrinsic flat sense, the mass seems to only be semi-continuous with work of Jeff Juraguy. But I don't know the asymptotically hyperbolic case, but Jeff Juraguy has proofs about semi-continuity.
Okay.
No,
with Dan Lee, sorry. And maybe
I'd like
Dan
to see that.
Here.
Yeah.
Dan Lee and Jeff have work on that. Yes.
Maybe give me a reference later, please.
Yeah.
Yes.
Thank you.
Thanks very much.
I will add that reference on the chat. Thank you.
Thank you, Christina. You understood the question. Yeah, that's the correct answer. Okay. And with this nice expression for the mass of a graphical asymptotically hyperbolic manifold, what Cabrera Pacheco showed, and this actually is very similar to Huang and Lee show, is the following. So if one studies the volume of the level sets of the function f, what one can prove is that this volume will be non-decreasing. And because it's non-decreasing, one can actually define this H0f. So H0f is going to be a height. So this is the height. And such that below this H0 height, all our level sets are going to have a small volume in comparison to the mass of our graph. Okay, so volume is going to be very small here for all level sets. And above that level set, what is going to happen is that f is not going to be very big. So actually the supremum of f minus this height h0 is going to be bounded by this expression that also only depends on the mass of our graph. Okay, so this is going to look in the Euclidean case, I would say flatter and flatter. So this would look more like hyperbolic space and hyperbolic space. Okay, and this is done, all this is done just by studying this function. Well, using this equality and studying the derivative of the function v. So one has to find a differential inequality, solve this differential inequality, or actually solve another a differential equation and then compare the solutions of this new equation with this inequality, okay? And one gets this nice expression. Okay, so once that one has these very nice results, as I told you before, Cabrera Pacheco show stability with respect to Federer-Fleming flat distance. So this is the theorem to take functions fi in this class that I define, such that the mass of the graphs with respect to fi converge to 0. And once one normalizes the graphs, so actually we want to have level set h0 of fi equal to 0. So we just vertically normalize our functions. Then what he can prove is that inside a ball, graph of fi is going to converge to the hyperbolic space of dimension n. So here I have hn times 0. Okay, and this is true for every r greater than 0. So he has this stability. Okay, and once that we have this stability result, well, one wonders, what about using intrinsic flat convergence? And one thing that I would like to mention is that, I mean, Federer-Fleming flat convergence distance or flat distance is an extrinsic distance. So here it really mattered that we were in Hn+1, as was pointed by Misha Gromov. So it really mattered that these manifolds were here, but intrinsic flat distance is an intrinsic distance. So it doesn't matter that they are in Hn+1, but it matters because of the geometric quantities that we will obtain given that our manifolds are graphical manifolds. But it's not important at all that they are in Hn+1. Okay. So what is the class that we are studying? So I already told you a little bit how this class looks like. So these are going to be manifolds M that can be embedded into the hyperbolic space. And actually we want them to be a graph of a function once they are in the hyperbolic space. And besides the conditions that Cabrera Pacheco put in these manifolds, we are going to require other conditions. Okay, so let me read these conditions. And first of all, we want the set U. Remember that the function f is defined in Hn minus d set U. And given a function f, there is a set U. So it's not the same U. The U's can be changing if I take a different function. But in equation 3, what we are saying is, okay, all these U's have to be contained in a ball of a given radius. Okay, so we want to control the interior where we don't know much about our manifold. And then to study the exterior of our manifold, we put the following condition. So outside these radial directions, we want the gradient of our function f, the norm of the gradient of our function f squared multiplied by v squared to be less or equal than gamma squared. So then this is going to give us like a Lipschitz, or by Lipschitz, a Lipschitz condition, decay condition outside of this ball. And one more condition that we need to study the interior of our manifolds, or actually what happens in our manifold in this region, is the following. So we want to define something that is called depth. And I don't have the picture here, sorry. But remember that our manifolds look like this. Okay, here I have this value, sigma R0, so it's this boundary. And omega R0 is all this interior. So with this condition, we are requiring that the distance from here, from omega R0 to all this interior region to be bounded by some constant D, okay? So this condition is actually required because remember, if one uses a Federer-Fleming distance, one can ensure, one can say, okay, I'm going to calculate my distance in a particular ball because we are in a fixed space. But when we use intrinsic flat distance, we cannot say we are going to just restrict ourselves to a ball. So we want to calculate a diameter bound for our regions, and this condition is going to give us a diameter bound for this part. And the last part is actually very technical. And it's the following. Maybe I make some comments later, but it's just technical. Mm-hmm. And as I told you, we want the manifold to have to be minimal or entire. And minimal could be something like this. But the minimality, we are just saying that along normal directions, we converge to infinity. And for tangential directions, we want this gradient to be bounded. Okay, so this is technical. I think it can be maybe removed. And let me continue to what follows. So that's the class. Are there any questions about the class?
I think it's clear.
Okay. So now let me tell you how the proofs go. And well, before how the proofs go, I remind you of the theorems that we want to prove. Oh, and here the G is missing. So I have a sequence of manifolds in this class that I just defined. And the mass is converging to 0. Then first we want to show that the regions, the omega regions, which remember are these ones, these are the graph intersected with this infinite cylinder, that these regions converge to the hyperbolic ball. And here I'm using, as was noticed, the intrinsic distance of these regions and of the ball. Though this ball is convex, so it's actually equal to DHN. Okay. And the second thing that we want to prove is that we can choose, or once that these points are chosen in this particular region, or actually outside of this region, one can ensure that the balls of our manifolds, so here I have the distance of my manifold, is converging to a ball in the hyperbolic space. And let me just tell you a little bit about this sigma j. So this sigma j is actually this. So let me write it. Sigma j is the boundary of omega j, which is this interior. And then we might have two boundaries, this exterior boundary and the inner boundary. So I'm taking away the inner boundary. Okay, so once I take a point in this part, what is happening is that in this region, I don't know if things are disappearing in the limit. I mean, one could have something that is getting thinner and thinner and thinner. Maybe this is not the right picture, but this region could be thinner and thinner and thinner, and in the limit, it disappears. So actually, I have to take a point here because points here do not disappear. And they do not disappear because we have this exterior condition. So once I take points outside this ball of radius r0 divided over 2, my points, I can ensure that points are going to converge and balls are going to converge. Okay, so these are the theorems that I want to prove. And this is the sketch of the proof of the first part. So how the omega regions converge. And as I told you, we are going to use the result by recall my theorem by myself, well, by Allen and myself, okay? So we want to use this theorem. This theorem ensures that a sequence MJ converges to M0, provided we have a diameter bounds, area bounds, the volumes of these manifolds converge to this manifold. And so let me tell you, no, this is the other way. And well, diameter bound and area bound. Let me just put it like this. Okay, so we need this. But one thing that I should mention is that remember that in this theorem, we actually fix the topology. So actually MJ equals M with a Riemannian tensor, and M0 is the same manifold. Oh, this is GJ with another Riemannian tensor, okay? And here I want to prove convergence of these regions that might not be diffeomorphic to a ball, and we want them to converge to a ball, okay? So they don't have the same topology. So because they don't have the same topology, what one has to do is the following. So we have to cap them off if the topology is not the same. But let me go back to the proof. So if the manifolds are entire, so there is a boundary of U is empty, then one can calculate volume, diameter, and area estimates using isoperimetric inequalities, co-area formula, and Penrose inequality. And one obtains these conditions and diameter and area bound. And moreover, because our manifolds are graphical manifolds, one will have that the hyperbolic Riemannian metric is less or equal than the Riemannian metrics of my manifold. And so then we get the required convergence, the convergence that we want. And if the manifolds are not entire, then as I told you, we have to carefully cap these manifolds. And when we cap these manifolds, this theorem, maybe it's a little bit too strong. This condition might be too strong, but as I told you, one can weaken this condition. And I can weaken this condition in the following way. So one can put an extra room for this inequality, and the theorem still is going to hold. Okay. So that's how one proves the first theorem. And the second theorem, which is convergence of the balls in our manifold MJ to the ball in the hyperbolic space, is as follows. So first, by the first theorem, one knows that these omega regions are converging to balls in the hyperbolic space. And now what one has to use is the nice properties. So the nice properties meaning this condition. So because we have this very nice control for the exterior region of our manifolds, one can actually show Gromov-Hausdorff convergence and intrinsic flat convergence of annuli of this type of annuli. Okay, so this annuli will converge to an annuli in here. This is a ball. Sorry, this is an annuli in the hyperbolic space. The only thing that might happen is that this distance is no longer the hyperbolic distance, but this distance is actually going to be by Lipschitz to the hyperbolic distance because we have this control. Okay, and once that we have Gromov-Hausdorff and intrinsic flat limit, given points pj's, remember that the pj's are here, then the pj's are here. So given a sequence of points pj's, there will be a subsequence that converges to a point here in this annuli in the hyperbolic space. Okay, and so now what we are going to do is we have convergence of these regions. We can take the restriction of this current to these balls, and they are going to converge to the hyperbolic ball as is here, restricted to this ball, centered at this point P infinity, because we have a convergence of Pjk to P infinity. Sorry, this should be P infinity. Okay, and once that we have this, well, we only need to check that these restrictions are actually this current, and that this restriction is this current. Okay, and then we have our theorem. And this is all. Are there questions?
Thank you very much for the beautiful talk. Does anyone have questions?